Hi everyone. I can't see you guys on the side. Unfortunately, I can't make it. And I'm Hongyang Li from the University of Hong Kong. And today I'm gonna deliver a talk on the end-to-end autonomous driving, past, current, and onwards. So my talk consists of four parts: the introduction, and also we propose a conceptual level idea called the word engine, what we call the end-to-end tool. And also, my talk will involve recent progress, including three recent works from our group about on the scene generation and also multi-traversal Gaussian splatting for the scene rendering, and also how to fairly evaluate or benchmark the autonomous vehicles reliably. And the last part deals with some key challenges on this field. So the definition of the end-to-end auto driving, so it's learning a single model that maps the raw sensor input directly to the driving scenarios, and it replaces traditional modular pipeline with a unified function. So here the function means given the observation or the target goal, we directly output the control. And here, the observation, you can say the image, the point clouds, or the vehicles, right? And the controls, it deals with the steering or brake or throttle. So the training pipeline is very simple. You can either use supervised learning with many annotations, or you can say the imitation learning, or using the design the reward and use the reinforcement learning. Okay, so here is a setup. And also we draw a very straightforward pipeline roadmap. So we can call it in the early days, I believe this dates back to the more than 20 years. So it's a very simple input from the black image drive-by-wire interface. And also through the years, we can see a bunch of methods. You can group them into different categories, whatever is a conditional imitation learning or generalization or the other interpretability where the network uses multimodality from the Andres Giger's team. And also we have the PPGL and also self-D ACT, ACO. They all works on the pre-training stage. So until recently, we have some explicit methods where the modules are still explicitly designed. You have the tracking, you have the mapping, and also the planner. But this is where we call the modular end-to-end planning. So for more details, you can check out this fantastic survey paper here. Of course, this is an incomplete list. Last past years, so we're all working on the for the end-to-end like 1.5. The reason we want to name it 1.5 is roughly defined by the number of corner cases resolved. I mean, so obviously, autonomous driving, the research has entered into the second stage where you're going to deal with massive amount of production issues, engineering efforts, right? So since the work of UNAD, I could roughly say that we enter the era of foundation models. So the most foundation model, the upper level, deals with the diffusion or using the diffusion pipeline and also the word models. We can see the drive dreamer, or we can see the Cosmos Predict 1, and also the navigation word models. I believe this is year's finalist paper, right? And also the GenAD Vista paper, they utilized given the multi-view images and given the different actions to predict the different types of videos to generate realism and also the diversity. And also we see the Gaia 2, which is video generative models for safer assistance and automated driving. And in the lower part of this slide, we have seen a lot of LLMs. For example, the Drive LLM, they propose a graph VQA to get a better understanding of the driving scene, and also the Lingo tool, and also this Drive VLM. I believe this is a very early work for the dual system in auto driving, where to utilize the better accuracy of the foundation model, but it has a heavy latency, right? So this is where the smaller model steps in to predict, like for most cases, and the both two systems leverage together. And we also see some examples in the robotics, right? And also this same lingo, I believe this is a very recent work, closed loop driving with language. So what's next for the end-to-end autonomous driving? I mean, if we could define the second generation. So the development here, we show the stack of driving models. This is a typical training and deployment pipeline where you got the data collection part. It's usually driven by the experts, and you collect the data, got to the training stage, and you train on the fixed log and play. And also you got the evaluation, and you have many feedback rate from the inference and collect more data, especially for the bad cases. So the question is, can we collect all the corner cases or edge cases, you could say that, and make it really a product towards the L5 or L4 eventually? So here we have some facts. I really like this website. I believe many of you come from the industry and also see the website here. It's called the Tesla FSD tracker. Basically, it collects many customer data on the website, primarily in the North American cities. So this figure shows the distance to the critical disentanglement of Tesla FSD over the different versions over the years, right? So you can see the MPI got increasing, which is very promising. That's good. But here, this is a figure. I think this is a motivation from the our recent work, recent project called the word engine. So here, the x-axis means the normal driving and also safety critical or near miss events. And if you drive very far away here, you're gonna run into the accidents. And the y-axis shows the we have two y-axis. The black curve is the occurring probability per mile to show the dangerous cases. And also, you're gonna see the red here is the deployment cost. So as we enter into more, like most of the perception problem have been already resolved, right? So the chance of uh, running into the challenging case become very rare, but the deployment cost becomes very expensive because you're gonna have a large fleet to collect all the dangerous cases, right? So we argue the remaining 20% of long tail problems require an excessive amount of data. So the reason is, can we collect all the corner cases? I mean, valuable corner cases become increasingly rare, and collecting data on dangerous driving can risk lives, right? So here we have this very, yes, the very conceptual pipeline called the word engine. This is a very high level concept level figure here. So we have the data collection. We want to learn from the human, right? So learn from the expert driving. So the policy is still the end-to-end planner, whatever is UniAD or VAD or other end-to-end given an arbitrary end-to-end algorithm. And through the environment with the vehicle, you can use call it the word model or engagement with the environment given the current prompt or actions, for example, turn right. We want to learn from the failures and improve the current end-to-end planner and make it shapeable for the production. So the key question is how to generate these value corner cases. The very key part here is to I think consists of two parts. So here, this is a corner case generation. Given the source scenario from the raw data, we want to generate the safe critical scenarios. This is a generated part to saving a lot of cost if you don't have a large fleet of cars. And this is on the behavior level of word model. Basically, it means given the trajectories, you want to model the behavior modeling between the environment and with your ego vehicles. And then once you have the trajectory, you want to render the things. This is what we call the generated or rendered rendering videos. So this is a sensor simulation. So through this feedback, we have this data engine to generate a lot of corner cases scenarios. And then we have the algorithm engine, which is not drawn here, is simply because it's work in progress. So altogether, these two parts, I mean, the data engine and also the algorithm engine consists of the word engine whole pipeline to improve an arbitrary, I mean, the end-to-end algorithm. So the third part, I'm going to go into the details about the recent progress as to the data engine part, where we have the scene generation called Nexus and also the MTGS multi-traversal Gaussian splatting. So here, this work is called Nexus, Decoupled Diffusion Sparks, Adaptive Scene Generation. So the task here is given map information and also the historical full scene agent states. So the agent states can be the trajectories of the agent from the past. The output is to generate the future agent states. I mean, the states can be waypoints, velocity, or dimensions, or you can simply imagine this is a motion prediction or trajectory prediction task. But here we want to argue that the key challenge here is so the synthetic scenario generation is to balance the reality and also the control. So this is we start from a simple diffusion policy. So as you may know, so the full screen so the full sequence denoising is gonna achieve the goal orientation. I mean, it has a very clear target, but are rigid and cannot react to dynamic environment changes. And we also have this next token prediction. This is another pipeline lineup of work, so which resembles GPT-2. You have are very reactive to changes because you predict the next tokens, right? But can easily lose track of the long-term goal. So we want to combine these two properties, which is reactivity and control here. By assigning each token in the sequence an independent noise level, we can treat them differently during the generation, which we group them together, group them into two categories, which is low noise tokens, provide strong guidance, ensuring long-term control. And another group is the high noise tokens, grant freedom to adapt, ensuring real-time reactivity. So here in the Nexus, we want to bridge the gap between the reactivity and also the controllability, reacting to real-time changes, while also the agent knows the whole long horizon. I mean, in this term, the predefined goals, the target point you are gonna go. So as to the framework for this goal orientation, we have the agent tokens are encoded with time and denoising steps. And then they interact with the maps and the dynamics via the attention. I'll skip the details due to the time limit. So, in a nutshell, Nexus uses a diffusion transformer and also the schedules tokens with varying noises level to control the generation process. So here, this is a very brief report. So we can see Nexus significantly improves planner performance and also the simulation realism in terms of ADE or other metrics in the motion prediction part. So Nexus full means we also generate so the whole experiments are done on the new plan datasets, and also we specifically generate a lot of more training data deals with the safety concerned properties. So this is what we call the Nexus full. So basically, you can see this is trained with a larger training data sets. And visually, you can see this is a scene that the Nexus generated as the corner cases. For example, here a vehicle overtakes from the right rear of the Eagle car and moves to the front. And also another work is called the multi-traversal Gaussian splatting. So this task is very simple. So basically it's a reconstruction from the single traversal. It's limited. So we can see we have the original view, existing work on the driving scene reconstruction suffer from the view extrapolation. So the main reason is forward motion, less view constraint, and also the repeated texture. So how are we gonna solve this? So here, this is a teeter figure in the original archive paper here. We just released like 3 months ago. So multi-traversal data from daily commutes. I mean, for the single pathway, like from your work to your daily home, right? So, for the same road, you can commute multiple times. So we can collect this data as the effective view interpolation cross lanes. But there's going to be lots of challenges. For example, the various appearance as in the shadows and the light, and also the transient dynamics. For example, the moving, the parked vehicles. So here, okay. So these are the results. Uh, these are the pipeline here. We have the multi-traversal data and also the LiDAR guided exposure alignment, and also the other training part, like how are we going to utilize all the losses to reconstruct the scene. So first, we will have this reconstruct a scene graph with a shared static mode. And also we have this appearance mode applies to the traversal specific appearance effects. And also we got the transit nodes, put the cars on the ground. These are the visual results. We can see here is the MTGS results. You can see based on different training segments, it can so it can reconstruct scene with very realism, and you can traverse with a large space. I mean, across even to 10 meters from the right to the left. And also deals with unseen scenario. You can see those are all generated scenes based on the losses or the other pipeline I just briefly mentioned earlier. And also, this is a visualization of the high-risk scenarios generated from the Nexus. And the last piece of work is the pseudo-simulation for autonomous driving. So this is a collaboration work from the Andres Geiger, NVIDIA, and Bosch, and our team. So basically, what do you mean by the V2, the second version of NAVSim? So here we observe that open loop evaluation, especially is on real data. This is a good part. And also it's compute efficient, no sensor rendering, and allows parallel model inferencing. But the downside part, it doesn't model compounding errors, right? So this is basically the very essence distinction between the open loop and the closed loop. And it also doesn't model the causal confusion. So here, for the closed loop evaluation, the good part is it models compounding errors. Subsequent inputs become very challenging with poor initial actions. And also it models a causal confusion. So historical motion insufficient for planning, but it's on the synthetic data and it's compute intensive, which means it requires a sequential sensor rendering and also requires a sequential modeling inferencing. So we want to merge these two parts together. So this is why we propose the pseudo simulation. So the pseudo means we have two stages. So on the real and synthetic data, the real part is the like the A, like this is the red self initial observation. You can see the ego vehicle observation based on the planning. So from the red to the green, this is a stage one real trajectory, okay? And the stage two is a pre-generated synthetic part. So you can imagine there are lots of possible observations based on planning, right? So in this example, we list the three trajectories, which lists as a B, C, D. You can also set up this hyperparameter as 10 or 100. So given this example, we have the purple one. Purple one means synthetic observations is pre-generated with the method called MTGS in the second piece of work I presented earlier, or other 3D Gaussian splatting work. So the combined score, this score is what we call the PDM score to evaluate any end-to-end algorithm performance. So the score is combined or multiplied by the green real one with the different weights. So different weights here is the green one is a true vehicle, right? So the nearer you close to the true distance, the larger weight you're gonna get. So in this example, so you can see three purple B, C, D, right? So in this example, the D part, this generated synthetic one, got the closest distance with a green one. So it's got a larger weight combined with the score that's generated by the trajectories from the algorithm. So this is a score that we called the PDM score, and it inherits all the good merits from both the closed loop and also the closed loop for sure. And also recently, we hosted this NAVSim V2 end-to-end challenge. It's hosted at SCCV in this October. This is a poster. I really want you guys to have a focus on the details, or maybe the participants, maybe the leaderboard is online pretty soon, and to keep an eye on the latest development in this field. Okay, the last part, I still got 5 minutes. Okay, so the key challenges, I mean, here I want to list out just one challenges. Is about the RL reinforcement learning, because I really think the end-to-end realm deals with the large scale of data, right? You can leverage unlabeled data and pile up all the large scale data to learn more, like drive like a human without resorting to many intermediate like perception or the other intermediate modules, right? So here, this part, how many RL training iterations are we needed for a robust end-to-end auto-driving? You can say, call it L4 or L5, whatever the engineering people or the industry will define. So here, recently we saw a very good work. I believe it's from the Valadan group. It's called the Robotic Autonomy Emerges from Self-Pay, also published recently. So the issue is the RL training in simulation is about nearly 2 billion kilometers. That's an analogy from the distance from the sun to the Saturn. It's even very far away. So if you can traverse all the distances in this universe, in this Earth, sorry, so we cannot resolve the autonomous driving problem given the conclusions here, right? So, but it got very promising results. I mean, finally, eventually, it will results and zero shot on real world data sets with nearly zero collisions. That's the very good part of the reinforcement learning. But in the beginning iterations, it got the sample efficiency problem, right? Literally every RL algorithm has it. So the very not ideally part is it assumes perfect perception. I mean, in this work, because it starts from the trajectory input part. And also it's a simulate scene representation and needs too many examples, right? So the question boils down to, do we need to train nearly 2 billion kilometers for a robust end-to-end policy? And here we want to argue that no, it's really not. And corner case example, if we do a very quick calculation, one case, we nearly need more than 200 miles sampling for the robust Tesla FSD, for example. And also it deals with dense reward learning in pseudo-simulation. It has to learn from multiple parallel futures. This also may lead to the computational concern for those work. So the future work as to the algorithm engine, which I didn't cover at all in this talk, it deals with how to scale up the RL algorithm to have this dense reward to improve the end-to-end algorithm. Altogether makes up the whole storyline of the word engine. So given the talk at the end, I may have some takeaways. So the first is end-to-end auto-driving has made great efforts over the years. Word engine is the next generation for the end-to-end auto-driving. But in this talk, I really have this give this very high-level concept. I believe more works are coming in the second half of this year. And also the Nexus is deal with the controllability and reactivity to guarantee both the good parts to generate the corner cases on scene behavior level. And also we propose this MTGS, which consists of the data engine part to ensure multi-traversal realism in large space. And altogether, these two data engine consist of data engine to generate challenging cases for the dangerous scenarios, for example. And the last takeaway is scalability emerges from efficient sampling. For example, the dense reward design in the RL to make it scalable from the data engine. So I'm really happy to have all the teams. Thanks for them. Many of the work comes from my students, and also Chonghao will be the author of Centaur will be at CVPR on site. So we are happy to take any questions. So this is the end of the talk. Thank you.